Okay.
It's not rollovers.
Okay. All right, so let me begin with the recall where we ended up. And it was perfect timing in the sense I couldn't discuss this at all. So we get to talk about physics today. Please check. And I think I used CT. Show Y. And with that in mind, let me rewrite this as a beta CT. Okay? So beta is the dimensionless ratio of V over C. V of course, is the magnitude of the moving observer. And this gamma is a constant, 1 over. Okay? So this is where we start. First, a little technicality, and then we'll talk a little physics. If you look at the expression for gamma, this is classical, this is real physics. You can't have complex numbers. So what does that immediately mean? Beta squared less than 1. Right? Which means, well, minus 1 beta 1. This is V over C, so minus C. It looks like if observers are able to move with a relative speed V compared to another observer, the speed of the relative observer has to be what? Less than the speed of light. So you already get that result that no observer can travel at or even beyond the speed of light. And you'll get infinity. Okay? Second thing, remember we kept on swapping the point of view between x and x bar by replacing v with minus v. Yeah? So if you do v, so that's 1 point. And if you do a swap, this of course means too many symbols. If I go back and forth here, that's like beta being swapped with minus beta. But remember, if you look at this expression, gamma remains the gamma doesn't become, for example, minus gamma or something else. Yeah? So that's good. We never allowed that to happen, but it just coincidentally worked out. So I mentioned this, I don't think it's mentioned too often, but what we did was not a proof. It was something, right? But what did it allow us to do? If we did the limited case of if something is traveling at the speed of light, photon, that means the moving observer is also observing that object to be traveling at the same speed. That is what it allowed us to do. We generalize this in a much more elegant way. When I say we, very often I mean the collective we. It means you will generalize this in your homework. Okay, good. Now let's look at physics. Oh my God, this is crazy. Because T is not equal to T bar. One person's clock simply doesn't tick like the other person's clock. You just came with a quick algebra, but these are the things I would like for you to reflect on your own time. So this is Friday evening. By the time you have your second glass of whiskey, you start pondering about stuff like this.
It's okay if I do rum instead.
Rum is fine too.
I'm 21, I can agree with you now.
True.
Okay, so we'll see. Today we'll see, lots of nice results. So that's what it is. I wanted to, yeah, so in this transformation, what I have sort of silently assumed that you have one observer, and the second observer is moving with the speed v along the x-axis. So you can imagine, really, I should add to it. And if I add to it, because space has x, y, and z coordinates, I should have completed this by saying nothing happens to y and z. Why did I choose the x-axis? Well, for convenience. If I did it between a relative motion between the y-axis, how would this change? This would be y bar, and this would be y, and x and z would be here. I could do this with z, and with a clever rotation matrix, and we'll do this, you could do it in any direction. You don't have to go in the x direction, y direction, or z direction. You can go in any direction. So we will generalize it to that level, but when you're doing a problem, guess what? If somebody's moving in some direction, you rotate your axis. Just save math. I mean, save trouble, right? Just point it along x. So it is with that intention that we picked this sort of a nice complex. This is a sample Lorentz transformation. This is called the Lorentz transformation. Quickly check something. Okay, so the other point is now we're going to locate points not in space, but we want to be very specific. We want to locate points in space-time. In the past, space-time was unnecessary. You have a clock, I have a clock. If we know when we start the experiment, our clocks are the same. Okay? So we can't do that anymore. We're not able to separate that. Really, one person's space is another person's time. And that's what we're going to see today. Okay? A little bit of notation. So space-time. So my coordinates are no longer x, y, and z. It is x, y, z. I could put t here, but I won't quite put t. I mentioned this. What would I put?
CT.
CT. Why would I want that? Everything has same units. Everything is distance. Yeah, meters or light years or whatever it is. So as you know, in the notes, there are lots of homework problems, but sometimes if the result of a homework problem is important, I'll state it to show you the importance of that problem. I think this may be the first problem. So here I wanted you to show that suppose you have in one coordinate system a beam of light traveling, except now we're not picking the x-axis, just any axis. So you can tell, and if this is the point, point 1, and this is the point 2, I would have c squared times t2 minus t1 squared equals x2 minus x1 squared plus y2 minus y1 squared plus c2 minus. Correct? I just squared it because it could be plus c or minus c. So when you square it, it goes away. This is sort of the Pythagorean length squared. So if v equals, if c equals delta x over delta t, c squared equals delta t squared, and the other side would have delta x squared. That's what you see. What I've asked you to show is if this is true for any 2 points, I take this and replace, I want you, so one of the problems is find the inverse. Well, I can change it. If this is true in a bar coordinate system, it's just as easy. Right? Some observer measures that. then I want you to show that this implies what? Correct? So this time, the second observer is still moving in the x direction, but you could shine your laser beam in some crooked angle. So now the tip of the beam, if you will have x, y, and z coordinate, because it's just going off at some skewed angle. It doesn't matter. Still, you will find that the speed of light formula is true. Simple algebra, just insert, replace t bar, x bar, y bar, z bar with everything on the right-hand side. And you'll see everything cancels off and you'll get that nicely. So again, regardless of the direction you send your photon torpedo, Lorentz transformation applies. Yeah? Okay. Today we're going to draw some nice diagrams to see what it means for space and time to behave in this way. If we use this algebraic expression as our anchor, that's not a bad thing to do. But you don't have a visual picture of how things can change. So we're going to talk about great effects like time dilation and length contraction. Again, chances are you've seen it in modern physics, but we'll draw a diagram. And depending on who you had, maybe they drew a space-time diagram. So here's mine. X. This is how, up until now, how did you draw something moving in as a function of t? Horizontal was we have inverted. The reason we have inverted is you should think, again, I'm not showing y and z. You should think of this as being all of space. And this space is evolving in time. I want you to change how you view these graphs. It's not a graph anymore. This is looks like a graph upside down, but this is really space evolving in time. So now what I'd like to do, if you're very quiet, familiar stuff I know, but any questions? Huh?
His head's in my way. Thanks.
I want to draw the t-bar axis because I can draw it. Because if I know x and y, x and t, I know t-bar. So I should be able to draw it. So to draw these axes, how do you figure out what x-axis is in this diagram? It's a set of all points where t is 0. Correct? If you said t equals 0, you get this axis. How do you get the time axis?
X is 0.
X is 0. So to get the t-bar axis, what do you need to do?
X is 0.
X bar. Correct. So t-bar axis. Set x bar equal to 0. And that's easy. It's just x is equal to beta c t. Because I'm setting x bar equal to 0. This is a constant. So it's a set of all points that makes sense. Yeah? But listen, we have drawn the graph upside down. So we have to make this upside. Get used to that, huh? This is like y, no, it's not y, but you know what I mean. This is like the vertical axis. So what equation is this? C is a constant, beta is a constant. Ct is like y.
Oh, this is just a function? Or non-function?
It's a function.
Yeah.
What kind of a function is this?
That's a linear.
I'm sorry?
Just a linear one?
Linear function. So the graph of this will look like a line. What kind of a line? Can you tell me what the y-intercept is? It's not y-intercept.
Zero.
Zero. What's the slope of this line?
1 over beta.
1 over beta. Beta is less than 1 in magnitude. So 1 over beta is
No.
greater than 1.
Greater.
So to do this, let me draw this guy. Slope equals 1. What does that mean? X equals CT, like slope. First of all, what is this line? What is it what is it showing in space-time? If something is doing X equals CT, what is that something? It is, yes, yeah. Later on, we define geometric objects. This will be called a light vector. It is light. So this guy, the time for the other observer cannot be light-like. It is a slope that is greater than 1. That has slope 1. So I think my graph would look like so. And slowly build into a shape.
And it can't go lower than X equals CT.
Yeah,
Yeah,
that'd be faster than speed of light.
correct.
You can't do that.
Correct. Exactly right. Exactly right. All right. So let's do.
Would that mean that X bar would just be orthogonal to that?
I'm sorry.
Would X bar just?
It has to be orthogonal,
Has to be orthogonal.
except there's a small problem. Let's see what. You're absolutely right. Okay. Let's do it. Good. Set what? Tell me, what will this look like? Solid. Put t bar equals 0. I'm sorry? Almost orthogonal. If they were orthogonal, what would it do? If you have two lines that are orthogonal, what is the product of their slope? All right, you people of relativity, let's go back to high school algebra. If you have
Zero.
Negative 1.
Negative 1.
Because it has to be the negative inverse. So,
Okay.
So, here, what's the product of the slope?
positive.
Positive 1. You will find that negative 1 and positive 1, this negative side will plague you this entire year.
Distorts, plagues us.
Yeah. Time goes in the negative direction. So it looks like that, same sort of an angle, but it's almost like this observer's lines get squished. So are your eyes, Veronica. They're getting squished as you look at the picture. What's unclear?
I'm just trying to visualize the line.
Yeah, we'll slowly unpack it.
Yeah.
Yeah. Okay, so what I want to do is I just don't want the x-axis and the y-axis, but I want to know x bar equals 0, x bar equals 1, x bar equals 2, x bar equals 3, so on and so forth, and y bar equals, t bar equals, ct bar equals 0, 1, 2, 3, and so on and so forth. If I wanted to do that, I could add a constant over here. I think in my notes, I must have picked a b here and an a here, just to move things up and down, right? If I did that, oh gosh, I'm gonna draw it, David.
I believe in you.
parallel to this guy. That's what I'm trying to do. Now I need, so this is, of course, t bar equals 0. This is like t bar equals c, t bar equals some constant.
You want to go over that again? It's kind of hard to see on, it's kind of hard to see right now. so I'm
Yeah, I
trying
know
to
with the
see on
chalk, it's a little dim, yeah.
Yeah, I was not confident in my drawing.
That's pretty good.
So I was trying to hide my deficiency. And then I have a cheat. I'll tell you what it is. I need to do the same thing. Okay, say this is t bar equals 0. This is t bar equals, say, 1. So this is x bar equals 0. Now I want to do x bar equals 1. And tell me why I think this. My notes has a much better picture. I want you to look at it and stare for a while. And I could draw multiple lines like this. So I could draw, if I didn't want to, if I wasn't worried about making a mistake, I would draw another green line like this, and I would draw another orange line like that. Okay, but the point is, and this is how you would locate points in x bar and t bar coordinate system. But look at how this kind of nicely worked out. So it intersects. If it's a constant amount, it intersects exactly so that both observers sees the speed of light to be the same. Yeah. So x over ct has to be, or ct over x has to be 1, equal portions. Yeah.
So it's not just that they're intersecting with each other, but also with x equals ct.
But x equals ct. If you go equal amounts, because x bar has to be equal to c t bar. So you can see what space and time is doing. It's progressing in such a nice way. Again, easy to draw a diagram, even though it's not very pretty, but a lot for you to unpack, right? Think about it over the weekend, please do so. And I could draw multiple lines, but you can see how speed of light will be preserved. Look at the notes for a better picture. Yes.
If you just say x bar equals ct bar, you'll just get the exact same line as x equals ct.
Correct. That's it. X equals ct means x bar equals. No, it's important.
And that's why for any value of x bar or x, it'll adjust along the line.
Correct. Yeah.
You'll always get an intersection.
So for light, you have equal portions of ct as you have of x. They move in tandem. Well, light is the balance of all of this. Okay? All right. I don't know if I need a definition at this point. Well, first of all, please let it be so consistent with my notes. So here's an example of time dilation. We get right in. Like I said, we started slowly, but we move fast. No pun intended. So this is a problem that's worked out in your notes. But, and it's written out in your notes, but let me describe it. So once again, here I can afford to be easy with my drawing. You have, I think, a spaceship or a plane, something fast, right? So very often I say a fast plane or a spaceship or something like that. But in this case, you have a rocket ship leaving Earth and going to a distant galaxy. So unnecessary middle line so that no one sees it for me to get a scale. But then this is what the spaceship does. So it travels a distance. I'm going to constantly suppress y and z. There's no need to do this. So if this point is 1, and this point is 2, I will have c times t1 equals 0, x1 0, and then c times t2 is some time t. It gets, so this is where the distant galaxy is, right? Doesn't look like a galaxy now, does it? And I would have x2 equals some t. And this rocket ship is moving with the speed v. If it is moving with the speed v, time and distance is related by the simple formula. Correct?
Should that just not be C there then? Should you not have CT in there? Because
Oh, right, very good, very good.
Yeah.
CT would be C times B.
Yeah.
Yes. No. Good point. Oh gosh, I like the C next to,
It is nice, yeah.
yeah. All right. So what we want to know is this rocket ship. So here's someone standing on Earth because this is this perpendicular nice coordinate. Here's my stationary observer. This guy is just, he wasn't, you know, they're the twin paradox twin, right? This twin didn't really go to college or anything like that, so he's not an astronaut. He just stayed back home, right? So the other twin gets on a rocket ship and goes to a distant galaxy. I'm sure you know the story. Now we do it diagrammatically. Let's find out the same coordinates in the bar coordinate system, which means this is, why did I draw the line this way?
Show it's going slower than the speed of light.
It's going slower than the speed of light. So it's above that 45-degree line.
Speed going back.
Yeah. Okay, so what does the astronaut twin measure? So here it is. Well, it's a wide ponytail. Okay? They synchronized, the twins synchronized their clocks when they got started. 0 goes to 0. And x1 bar is equal to 0. My question is, what is CT2? Well, I've got my handy-dandy relativistic clock converter. And so I would do C2 equals gamma times CT, right?
Yeah.
Minus beta times D. And so I have C2 equals gamma times CT, and then I'm going to use minus beta. Instead of D, I'm going to do B times T. Correct? And so, what do I need? Beta is, am I missing a T somewhere? Correct. So I guess I can T2 bar equals gamma times 1 minus beta squared times T. Sorry?
That would just, or be 1 over gamma times t.
That would be correct. T2. If you're going below the speed of light, what is gamma?
Greater than 1.
Is it more than 1 or less
This
than
would
1?
be less than 1.
No, 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 it's 1 over a small number.
So it'd be greater than 1.
Yeah, see, beta, the smallest beta can be a 0. When it's 0, gamma is 1. When beta becomes non-zero, this number is less than 1.
Yeah.
So square root of that number is less than 1. When you divide by something that is, divide by so the gamma becomes more than 1.
So T2 is a smaller amount of time than T1.
Yes, T2 is less than T. Now, this is half of the twin paradox. We're not. So what happens if now the twin that's reached this distant galaxy comes back around? All these numbers get multiplied by 2. Depending on how fast the twin travels, their ages are going to be different. Twin returns, this person is older, twin is much younger. Literally, only that much time would have passed. There's nothing gained or lost by either of the twin. They've only lived that long. Our clocks do not agree. Moving clocks do not agree. Looks there. Let me see how it looks next. Maybe in definition or so. In the notes, definition 1.1 is called, defines what's called proper time. I won't write the definition down, but let me describe it. I invite you to look at your notes. Proper time for an event is the time measured by the observer for whom the event is stationary. Yeah? And and proper time is denoted by tau. Again, I invite you to read my definition a little carefully. And this is not so clear what we mean. It depends on what is being asked. Suppose this twin were to return back to Earth. Who would have carried the proper time?
The twin was on Earth.
The twin that was on Earth. Because the problem begins on Earth and ends on Earth. And so the twin was always on Earth. Suppose that, let's do 1/2 of the problem. Let's do exactly this case scenario. Beginning is at the origin, which is x equal to 0. End of the problem is at the galaxy, for which observer is both the starting point and ending point at the same x, the one on the rocket. So for that event, the proper time is the moving twin. Let's verify that. Let's do x2 bar. So that is gamma x, which is, d minus dc t2. What was t2? T2 was t. guess what?
We use just CT. Yeah, so we get CT minus, or VT minus VT.
D equals VT, so D minus VT is 0. So for this moving observer, the bar, it begins at x2 equals 0 and ends at x2 equals 0. That's fine, because we just drew that. This is the line, x bar equals 0. I know what I've done. I've taken a simple explanation of a nice problem and made it slightly messy in your mind. But I want you to unpack it.
So you think is any observer is stationary and everything else is moving relative to it?
This moving observer.
For the moving observer.
But for the moving observer, the beginning is when x is equal to 0. End is also when x is equal to 0. So that person reaches the galaxy and goes, oh, wow, look, it's right here. It's at x2 equals 0. When I started the problem, I was on Earth. Oh gosh, it was again at x1 bar was 0.
It's not necessarily the stationary person, but it's the person whose distance from the point being calculated. is
Correct.
0.
Yeah. Don't worry so much about the notion of what's proper time, but what I would like for you to do, if I were to ask you, what is the final time and space coordinate measured by the moving object? Can you find that out?
The space should be 0.
Yeah. I mean,
Make sure all is zero.
you use this.
So from the moving observer's perspective, there's no telling whether they're the ones moving or everything else is?
Correct.
To them?
Correct. Yes. Yeah, it could be the galaxy coming towards you.
And Earth going away from you.
Yeah. And that's the thing about inertial observers, right? This is all constant velocity motion. So constant velocity, so there's a little bit of a cheat. I didn't say this is sort of a jetpack speeding up. Somehow this person, started moving and slowly sped up to that speed. That's when we're starting the experiment. So when you're already moving in space, you're just moving. You're off the gas pedal. Newton's law of inertia just carries you. So according to you, if you blindfolded the person outside of the initial acceleration and then remove the blindfold, they would feel everything to be perfectly still in the spaceship. They can pour a nice cup of coffee, and they would go, "Oh my God, there's a galaxy approaching." Engines turned off, no vibration, nothing. Right? It's like the whole universe is moving. But again, we'll slowly develop intuition for all of this. But this should be your anchor. Okay? All right. If time dilates, what must length do? Length contraction. So for this problem, I also define what's called, just like proper time, you need proper length. Proper length is much more intuitive. It's the length of an object measured by an observer who is not moving relative to that object. So if you're measuring, say, the length of a spaceship, yeah, it's just parked somewhere, then you step outside and you measure it. Yeah. So in this case, so I wanted to cover this in the second lecture, but I had some technical difficulties, but I didn't want to move this topic to the next lecture, so I'm just adding this on as an edit. What I want to discuss today is length contraction. Again, this must be a topic that you're familiar with if you're studying modern physics. If something of a certain length, let's say a fast airplane or a spaceship or something that's moving, with a large speed, close to the speed of light, is moving past you. And if you measure the length of this object, its length is going to be less than the length measured by an observer that is actually sitting on the spaceship. So there's a definition here of proper length. It's very close to, it's the analog of proper time. So proper length is length measured by an observer which is at rest as compared to the object whose length you're measuring. So in our case, we have a spaceship, and here's my usual old flash coordinate spaceship, and you know the observer is inside the spaceship maybe, but he or she would then measure it as a proper length, and it's called L0. Now the question is, somebody standing here on Earth, what would they measure the length to be? By the title of the talk, you'll see that it's length contraction. So I've already drawn a diagram to tell you what's going on. So in this diagram, of course you have C and T, you have the moving spaceship. So let me fill that in. I have in orange the spaceship. And I'll explain. So it's the front of the spaceship. This is the front and this is the back. And it's moving compared to an observer at rest. And this observer, well, rather rest in this sense. This observer is measuring CT and X. And then of course there's the moving observer, which is on the spaceship, measuring the spaceship sort of looks like this. And I'll explain why they look the way they do. Okay? All right, so first of all, the moving frame here is the spaceship. So we'll pick the T-bar, X-bar coordinate system for the spaceship. So as I mentioned before, this is the back of the spaceship, and this is the front of the spaceship. Let me write down Lorentz transformation as I remember it. And because we have to do the inverse, it becomes a whole lot easier. It is CT minus beta X, I think, and X bar equals gamma X minus beta CT. I think that works out. Beta is dimensionless. CT has the dimensional thing. Turns out we need the inverse transformation. So let me write that down over here. We know the recipe, and you have actually verified this in your homework. What do? We change the bars to non-bars and plus V to minus V. So in doing so, you'll get CT equals gamma CT bar. See, I'm switching the bars, and beta becomes minus beta, because the relative velocity is minus v. So plus beta x bar, and x bar equals, x equals gamma x bar plus beta c t bar. This is the inverse Lorentz transformation. Again, nothing going on in terms of the y and z coordinate. All right, so how do you measure length? So it's easy if the object is not moving. So I want to measure, the length of the board, let's say from here to here. It's not a big deal. I use a meter stick. And I just measure it out because I'm at rest compared to the board, parts of the board that I want to measure the length of. But if it's a spaceship, I mean, you start at one end, the other end is going to keep moving. So that won't do. So what you have to do is freeze frame. You fix a certain time and maybe take a real life image of it to scale. It's tricky to do. But in principle, that's what you have to do. You have to measure it at your same time. So let me explain the diagram first. If you are on the spaceship, a fixed time for you is your x-axis, or in this case, the x-bar axis. And that is why the diagram looks like this. And this is the moving frame, and the proper observer is in the moving frame, so this becomes the proper length. On the other hand, here you are. For you, an instant of time is a perfectly horizontal line. And that's what I've drawn here. So you can see, well, these two lengths are not equal. Now all you have to do, gosh, like we do for this entire chapter, is algebra. So you're gonna fix your time. So as you measure one end and the other end, your delta t has to be 0. Okay? Well, c times delta t, because it just comes together. Every time there's a t, there's a c there. So I'm going to take this equation and impose c delta t equals 0. When I do that, I get c delta t bar equals minus beta delta x bar. So for the moving observer, there is a delta x bar for the c delta t to be equal to 0. And that's very clear because x bar here is not the same as x bar there. All right, and then you want to measure your length. And this guy is L0. And for us, delta x, if you look at that diagram, I've called it L. All right, let's put this in. Delta x equals gamma delta x bar plus beta c delta t bar. So I have, let me do one more step. Delta x equals gamma delta x bar, and c delta t bar, I'm going to replace it with that, so I'm going to get minus beta squared delta x bar. Let me put symbols in. Delta x is the length you're measuring, not quite the proper length. Gamma, I'm going to factor the delta x bar out, so I get 1 minus beta squared. And then it's delta x bar, but we had agreed that delta x bar is L0. L0. And so, with what little space I have, you know, gamma is 1 over square root of 1 minus beta squared. So I would get L is equal to 1 minus beta squared L0, or L is equal to, and this is the result we want. Remember, gamma is greater than or equal to 1. When v equals to 0, gamma is 1. When v is non-zero, gamma is greater than 1. So you're taking a number larger than 1 and dividing it by the proper length, so you get a smaller number. Hence, length contraction. So we've seen time dilation and length contraction. So we're going to move on very quickly. In the next lecture, we're going to talk more about Lorentz group, and we're going to be very abstract. Any questions?